Dear students, in this video, we are going to learn about the definition of range, kernel, and theorem 1. Let T from U to V be a linear transformation. Then R of T is a subspace of V and N of T is a subspace of U. T is 1, 1 if and only if N of T is equal to 0. And definition of rank and nullity. Then theorem 2, rank nullity theorem. Statement of rank nullity theorem is, let T is defined from U to V is a linear transformation. Then R of T plus N of T is equal to dimension of U. So these are the concepts we are going to learn in this session. First let us take up the definition of a range and also kernel. Definition, let T from U to V be a linear transformation. See, we have taken the linear transformation from U to V and the range of T is denoted by R of T. So that is T of alpha such that alpha belongs to U. Range of T means it is nothing but the image set. See, T of alpha means images. Linear transformations of alpha means image of this one. See, T of alpha is alpha dash in this diagram. T of beta is beta dash. Similarly, all elements of U will have the images. Then kernel of T is denoted by N of T. N of T is nothing but the null space. See, here we have denoted a circle inside this set. See, this implies the N of T. This denotes N of T. See, whatever the element of U mapped with a 0 element is called as the null space. So nullity means it is nothing but the kernel. Kernel means kernel of T means the set of elements which are mapped to 0. See the diagram? Here we will have some gamma, beta, beta 1, beta 2, alpha 1, alpha 2, like this. Some elements we can consider in this space N of T. See, those elements which are mapped to 0 are called as the null spaces and that set is denoted as the kernel of T, that is N of T. See, this is the transformation defined from U to V and U is the domain and V is the codomain and the T of alphas is the range set. Range set is always the subset of V and N of T is the subspace of U because the elements which are in U mapped to 0 is known as the null space. T is 1, 1 if and only if N of T is equal to 0. If this space contains 2, 3 elements, then N of T will not be a unit set. So every element must have unique image. Then only we say that it is 1, 1. T is 1, 1. Now let us prove these 3 results one by one. N of T we have taken. This is the set of elements of U which are mapped with 0. So easily we can prove these 3 results. Now clearly R of T is a subset of V because every image alpha dash beta dash belongs to R of T. Then there exists alpha and beta such that T of alpha is equal to alpha dash, T of beta is equal to beta dash. From this diagram it is very clear that T of alpha is equal to alpha dash, T of beta is equal to beta dash. So alpha dash and beta dash are the elements of R of T. They are elements of V. Hence R of T is a subspace of V. So to prove that, let us take the linear combination. C1 C2 belongs to F implies C1 alpha plus C2 beta belongs to U. And also consider C1 alpha dash plus C2 beta dash is equal to C1 T alpha plus C2 T beta. Because alpha dash is T of alpha, beta dash is T of beta. Now taking the combining transformation, T of C1 alpha plus C2 beta belongs to R of, hence R of T is a subspace of V. R of T means it is image set. Then clearly from the figure it is understood that N of T is a subset of U. Let us see whether it is a subspace of U or not. So clearly N of T is a subset of U and let C1, C2 belongs to F and alpha beta belongs to n of t, which implies that C1 alpha beta are the elements of n of t, then their images are zeros. Now consider t of C1 alpha plus C2 beta, which is equal to t will take inside t of alpha plus C2 t of beta. Now since it is a null space, so t of alpha is 0, t of beta is 0, hence C1 0 plus C2 0, which is equal to 0. So when it is 0, it belongs to n of t. Hence C1 alpha plus C2 beta belongs to n of t, and n of t is a subspace of U. When this linear combination of C1 alpha plus C2 beta becomes 0, then it belongs to the null space. Then third result, let t be 1 1 and let alpha belongs to n of t implies t of alpha is equal to 0 dash. See, when you say alpha belongs to n of t, then t of alpha is 0 dash. So which is nothing but t of alpha is equal to t of 0, hence alpha is equal to 0. Further, this implies that n of t is equal to 0. So conversely, if n of t is 0, then t of alpha is equal to t of beta, which implies that t of alpha minus t of beta is equal to 0. Just we have transferred terms to this side. Then take t of alpha minus beta, and which is also equal to 0 dash. So which implies that alpha minus beta is equal to 0. Alpha minus beta is equal to 0 means alpha is equal to beta. See, when you take t of alpha is equal to 0 and t of beta is equal to 0, they belong to null space, then alpha and beta are equal. Hence t is 1 1. So this is the proof of the first theorem. Then definition of the rank and nullity. Let t from U to V be a linear transformation, then the dimension of R of t is called rank of L of t and denoted by R of t. See, the dimension of the range set is rank and the dimension of the null set is the nullity, which is nothing but from the diagram, the dimension means how many elements are there in this n of t will give us the nullity. Number of elements present in R of t, that is a range space, gives us the rank. Range space is a subset of V, nullity is a subset of U. So based on this, let us prove an important theorem, rank nullity theorem. Statement: t from U to V is a linear transformation, then prove that R of t plus n of t is equal to dimension U. So rank plus nullity is equal to dimension of U. This is n of t, linear transformation t from U to V, and this is R of t. So t of beta 1 is beta 1 dash, t of beta 2 is beta 2 dash, t of beta r is equal to beta r dash, t of alpha 1 is 0, t of alpha 2 is 0, alpha n is 0. We have taken B1, that is a basis B1 containing alpha 1, alpha 2, alpha n be the basis of n of t. So let us consider this is a basis of n of t. Then when we say that this belongs to n of t, then immediately it is understood that it implies that t of alpha is equal to t of alpha 2, t of alpha 3, so on. T of alpha 1 is equal to t of alpha 2 is equal to t of alpha 3, because the dimension of n of t is n. See, n number of elements will be present. See, B1 contains n number of elements, means its nullity is n. Then let B2 is equal to beta 1 dash, beta 2 dash, beta 3 dash, so on, beta r dash be the basis of R of t. Then the basis B will be alpha 1, alpha 2, alpha n and these elements together, the elements of U. That is, basis B is equal to alpha 1, alpha 2, alpha n, beta 1, beta 2, so on, beta r. We show that beta is a basis of U. That means to show that it is a basis of U, we have to prove these results. That is, B spans U and B is a linearly independent. So let us prove this one. We show that B is a basis of U by showing B spans U. B spans U means alpha is a linear combination we have to show. So let alpha belongs to U, then T of alpha will belongs to R of T, and T of alpha can be a linear combination of D1 beta 1 dash plus D2 beta 2 dash so on dr beta R dash. That implies that T of alpha is equal to D1 T of beta. See, beta 1 dash means it is T of beta 1. D2 T of beta 2 dash means T of beta 2. So by taking the terms like this, we get T of alpha is equal to D1 T of beta 1 plus D2 T of beta 2 plus D3 T of beta 3 so on dr T of beta R. Now T of alpha, so D1 beta 1 plus D2 beta 2 so on dr beta R. Then transfer these terms to this side, so we get it as T of alpha minus T of D1 beta 1 plus D2 beta 2 plus D3 beta 3 so on dr beta R is equal to 0 dash. Now take the transformation outside, so we get T of alpha minus D1 beta 1 plus D2 beta 2 so on dr beta R is equal to 0 dash. Now you see, transformation of this is equal to 0 dash means this element, that is a alpha minus D1 beta 1 plus D2 beta 2 so on dr beta R belongs to n of t, because the transformation of this element is 0 dash, so this belongs to n of t. Since this belongs to n of t, alpha minus d of beta 1 plus d2 beta 2 plus d3 beta 3 plus so on dr beta R can be written as C1 alpha 1 plus C2 alpha 2 so on Cn alpha n, because n of t contains alpha 1 to alpha n elements. So which implies that alpha is equal to C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 so on Cn alpha n, and add this to this side. Take this minus term to this side. So we get D1 beta 1 plus D2 beta 2 so on. Alpha can be written as a linear combination of preceding vectors. So alpha 1, alpha 2 so on, beta 1, beta 2 so on beta R. This vectors combination is C1 alpha 1 plus C2 alpha 2 so on, that is equal to alpha. So alpha can be expressed as a linear combination, hence B spans U. Then we have to show B is linearly independent. To show that B is linearly independent, we must prove that all scalars are equal to zeros. So consider this linear transformation, that is C1 alpha 1 plus C2 alpha 2 so on Cn alpha n plus D1 beta 1 plus D2 beta 2 so on dr beta R is equal to 0. Now take the transformation of this, we get T of C1 alpha 1 C2 alpha 2 plus so on D1 beta 1 plus D2 beta 2 so on dr beta n, that is equal to T of 0, because it's a linear combination and we know that it belongs to n of t, therefore T of this is equal to T of 0. Hence C1 T of alpha 1 plus C2 T of alpha 2 so on Cn T of alpha n plus D1 T of beta 1 plus D of T beta 2 so on is equal to 0 dash. So we have expanded this term. See, T of alpha 1 is equal to 0 because it is mapped to 0. So mapped to 0 in the sense alpha 1 alpha 2 are the elements of null space. So their images are 0. So C1 0 plus C2 0 plus C3 0 so on Cn into 0 plus D1 T beta 1 plus D2 T beta 2 plus D3 T beta 3 so on dr T beta R is equal to 0 dash. Now see, this implies that D1 T beta 1 plus D2 T beta 2 plus D3 T beta 3 so on dr T beta R is equal to 0 dash, because when you take alpha 1 alpha 2's transformations as zeros, these terms completely become 0. So this linear combination becomes D1 T beta 1 plus D2 T beta 2 plus D3 T beta 3 so on is equal to 0 dash. Now T of beta 1 is beta 1 dash, T of beta 2 is beta 2 dash, T of beta r is equal to beta r dash. So by substituting those values in this equation, we get d1 beta 1 dash plus d2 beta 2 dash so on dr beta r dash is equal to 0 dash. The sum of these elements are 0 dash implies that d1, d2, d3s are zeros because beta 1, beta 2, beta 3 cannot become 0 because they are vectors of V, images. Hence, d1, d2, d3 are zeros. When all d1, d2, d3 so on dr is equal to 0, B2 is linearly independent. Hence, the linear combination C1 alpha 1 plus C2 alpha 2 so on d1 beta 1 plus d2 beta 2 so on dr beta r is equal to 0. Since this is equal to 0 implies that C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 so on C1, C2, C3s are also equal to 0. Since beta 1 is equal to alpha 1 alpha 2 so on alpha n is linearly independent. Since it is a linearly independent set, its combination is also equal to 0. That is C1 alpha 1 plus C2 alpha 2 plus C3 alpha n so on d1 beta 1 plus d2 beta 2 plus dr beta r is equal to 0. Further, this implies that all constants are zeros. Hence, all constants are zeros. B is linearly independent and B spans U. Hence, these two conditions are satisfied, then B is a basis of U. Since B is a basis of U, dimension of U will be the dimension of N and dimension of R, that is rank plus nullity. Hence the theorem. Thank you.